All right, what is going on, guys? Today we are going to continue with conformal field theory. Today we are actually going to dive deep into something quite interesting, how conformal field theory relates to geometry. And let's go ahead and get started. Make sure to hit the like and subscribe button. Make sure to go onto my Patreon page if you want to support there. When you support, you get access not just to conformal field theory stuff, but also to everything else that's being produced. I am in the process of, again, making a website where there will be a library of advanced topics. I'm also in the process of making more biophysics-related stuff. And yeah, everything's sort of falling into place here. I think it's going to be great. It's going to be fun. So let's go ahead and get started. All right. Why do we want to talk about conformal field theory in the context of geometry? Well, conformally, Emmy Noether, again, if you study the history of modern physics, Emmy Noether was famous for her Noether's theorem, right? Noether's theorem, which stated that for every continuous symmetry of action of any sort of system, that corresponded to some sort of conserved measurable quantity, okay? So if you're familiar with this theorem, great. If you're not, you don't have to be that aware of this. But the point of her theorem was that in the context of physics, if you transform your system temporally, for example, a temporal translation, okay, you move your system from one time point to another time point, which is what all systems do, essentially. I have a plant right in front of me. It's always moving in time, even though it's not moving in space. It's the total conserved energy, or the total energy of that quantity, or the total energy of the system is the quantity that is conserved. Okay? Under spatial translations, the linear momentum is the thing that's conserved. And in rotations, you have angular momentum that's conserved for our system. So we have these conserved quantities, these conserved physical quantities, but now we're talking about conformal field theory. Now, conformal field theory incorporates this idea of conformal transformations. And these conformal transformations include temporal, spatial, and rotation, temporal and spatial translations and rotations, but they also include dilations and special conformal transformations, or translations, right? Dilations and these SCTs, I'll call them SCTs, maybe not, these special conformal transformations. Well, we want to know now, are there conserved quantities associated with these that are of interest to us? Okay. The answer is not going to be very obvious here. And some people speculate that the answer to these questions are going to be in high energy physics, because this is the conformal field theory is really the home of string theory. Like string theory and high energy physics is where conformal field theory starts mattering. And so the speculation sort of right now is we still don't know what these are, but they are probably associated, these translations are probably associated with some quantity that is really only observed on high energy levels, okay? But we can make sense of the geometry of these. So when you translate these, when you do these translations, temporal or spatial, if you have a coordinate system, we can actually look at these here. If you have a coordinate system and you spatially or temporally translate, you're conserving distances between points here, okay? When you do rotations, same thing, conserving distances between points. And when you're doing dilations, you're also conserving distances between points here, okay? And so this is quite interesting, right? So the point here is that so this is actually, yeah. So the point here that I'm trying to make, if I this point, this point, this point, and this point, those points are going to be that distance is conserved, right? Same thing here. This point and this point, this point and this point, those distances are conserved. Here, this is a little bit different. The thing that's conserved now is going to be, well, this point and this point, and then this point and this point, not conserved. So the distance, I think I oh, here. No, that's good. The ratios of distances are going to be conserved, right? So the ratio of this point and this point to, say, this point and this point, right? That ratio is going to be the ratio is going to be conserved under dilations. So you have to pick 3 points in that case, and when you do that, that's the thing that's going to be conserved. So ratios, and then the weird, pardon my French here, but the fucking weird thing with these weird special conformal transformations. What on earth is going on here? What we're going to do in this video, this is probably going to be a lengthy video, is we're going to dive deep into understanding this and this from a geometric perspective. Okay? The answer to this is going to be cross ratios of distances, and we'll get to that in a bit. These cross ratios are also sometimes called anharmonic ratios. So let's go ahead and get started now. So we're set up now to undergo this momentous task of trying to understand the dilations and special conformal transformations in the terms of geometry. So all the equations that we have seen are in their finite form for each transformation, right? So all these equations here, all these here, in a finite form. Notice for translations we need this a mu. For rotations we need this m mu nu. For dilations we need a scalar, and for special conformal transformations we need a vector, right? So here we need a vector, here we need a vector, here we need a matrix, here we need a scalar. Okay, so recall what we've done so far. We've established this equation. This is the equation that tells us what a new coordinate is like under a special conformal transformation. We can define then this b vector to be parameterized by time. Okay, and this isn't going to be super necessary, but this will help us understand something quite useful. So our b vector now becomes parameterized by time. By doing this, the coordinate transformation becomes a function of time. Right, so right here. Okay, we can now say that if this is just a constant, right, this is just our original point, right, that's just a constant. So the time derivative, the rate at which our new coordinate changes, well, that's going to go to 0 because this is not a function of time. It's just a single point that's not moving. It's going to equal all of this. Okay, so we have a prescription now for how the new coordinate transforms in time. We define a new parameter, a new normalized coordinate. Right? We could sort of think of this as an inversion, but not quite. I just like to think of it as a new normalized coordinate, right? So it's not like 1 over x or anything like that, but it's this new this coordinate y mu we're going to define to be x mu over x squared. So this is a point, right? So if we have some coordinate, and right, so our coordinate system, say we have a point here. This is x, our point x mu. X squared is just equal to x mu, right? So that's just so this can also be written as x mu over x mu like this. Okay, why do we do this? Well, we do this because when we take the time derivative now of this thing, well, that's just going to be we do the quotient rule. We do the quotient rule here, okay, and then we just then this thing here is this, right? Because that was this right here. Okay, same thing here, and then so from here to here, then we're just collecting terms and all this, and then from here to here, the point is that this here, the time derivative of this, is equal to this shifting vector. This shifting vector was this thing up here, right? So the time derivative of this is this, okay? This is going to be extremely convenient because what we've now found is that the time derivative of our newly normalized coordinate, not current, so our newly normalized coordinate is just the basis of our b vector. We can visualize this by saying, well, okay, so here's our coordinate. It time evolves in this way, so this is our original coordinate minus some, this could be plus, it doesn't really matter, but minus some change in our coordinate times time. Well, our change in our coordinate, we just calculated, was this, which is where y, again, is our normalized coordinate. Okay, so this is extremely convenient. This thing here is extremely convenient. This is going to tell us under a special conformal transformation, this thing just gets transformed linearly with time, okay? So under our special conformal transformation, our newly defined normalized coordinate transformed linearly with time, which is what I just said. This is great, so we can say this now. Okay, so because this, again, this is our normalized coordinate, and this is changing linearly with time. We can now take this equation, because we now want to isolate this thing, that we want to isolate this guy right here. So let's go ahead and do that. And when we do that, we write this, right? So actually, so this bit right here, that was just our b vector. We change that. Squaring both sides, we get this, all right? We expand this thing out to get this, and then doing just some algebra, we get this. More algebraic manipulations, we get this here, right? So this guy here becomes, this is going to get squared, right? So we're going to have x mu squared over x prime mu squared over x. That doesn't have to be primed, right? This is going to be x to the fourth, right? So this is going to go to 1. This exponent is going to go to 1 or 0, right? And then this exponent is going to go to 2, which is why we get this, because anything to the 0th power is just 1. And so we have this then. We have this then. And then this guy, we take the inverse of all of this and we get this. Okay? All right. So, okay, so we have this. We want to know the coordinate change though, right? So if we have this, then we can multiply, right? So if this is how our coordinates is, or how our normalized coordinate transforms, well, this thing here, we just multiply both sides by x prime squared. That's why I had the prime up here. The prime was supposed to be on the other side, which is why that confused me a little bit, because this is the newly transformed coordinate, right? So then we get this here, and so again, this is just, we're multiplying both sides by x prime squared, and then so we get this. X prime squared, we said, was all this, which is all right here. Okay, and then we multiply this out, right, and we get this right here. Okay, and so, right, because this times this is just that's going to cancel. So we have this here, and then our b times x squared right there, right? So, and there we have it. This is the rule that tells us how our coordinates transform under a special conformal transformation, right? Because we have now that x mu, this is x prime mu. That's how all of that changes. So if we want to get our newly transformed coordinate from our old coordinates under the special conformal transformation, this is how we do that. We now want to understand what is conserved here, if anything at all, under this type of transformation, right? So again, the idea being that we do the transformation, we want to know now, is there any sort of geometrical insight that we can get from this transformation that remains invariant? Because that's the key thing here that we want to know. What remains invariant under transformation? What is true under this, not true, but what doesn't change under this transformation? That's a symmetry, right? That's a symmetry or some invariant. Those are the things that are fundamentally interesting to us in physics. Okay, so this is going to be a mathematically very hefty section. So I'm going to give you this. This is the punchline, right? This is the punchline. The punchline, if you don't want to do the math here, you can stop here. The rest is going to be for those of you who contribute to the channel and who want to understand the details here. So under dilations, we mentioned that the ratio between distances is the thing that's conserved. So this is the prime side, this is the not prime side. Okay. For special conformal transformations, these things called cross ratios are going to be the things that are conserved. The reason they're called cross ratios, sort of mathematically, again, visually, if you visually want to understand this, you can contribute to the channel. I sort of see this sort of crossing happening right here between all the indices, and this sort of has to happen in order for this to work out. Here you don't need that, right? But here this is kind of a necessary thing. So with that being said, make sure to hit that like and subscribe button. I'll see you guys in the next video. For those of you who are not contributing, for those of you who are contributing, you can, if you're not contributing, again, you can contribute. So that's okay. Let's just hang that up, and I'll see you guys in the next video. Bye.